Good morning, everyone. For equilibrium and operating line problem of group 3, we have an absorber uses oil to recover benzene from a gas stream containing 8 mole percent benzene and 92 mole percent air. The gas feed rate is 100 kilomole per hour square meter. The oil fed to the column top, which is 80 kilomole per hour square meter, is benzene free. Equilibrium is given by y is equal to 0.45x. The desired recovery of benzene is 99%. Letter A, find the mole fraction of benzene in the oil leaving the bottom of the column. Letter B, what is the number of stages required if the operation takes place in a tray column? Letter C, what is the minimum oil flow rate for this operation? Letter D, if the operation occurs in a packed column, what is the number of transfer units or NTU as NOY? And lastly, letter E, if the packed column height is 3.35 meters, determine KYA in mole per second cubic meter. In letter B, we are required to find the number of stages graphically, and in letter C, we are required to find the minimum oil flow rate graphically also. We are given an absorber with oil or liquid fed to the column as 80 kilomole per hour. We don't have any mole fraction given here. For the gas feed rate, we have 100 kilomole per hour and mole fraction of 0.08. We don't have any given product gas and product liquid. We are required to find the mole fraction of benzene, the number of stages, the minimum oil flow rate, the NTU as NOY, and KYA if the packed column height is 3.35 meters. Using these equations here, the material balance is LO plus VB is equal to LB plus VA, and the component balance, we can use this to calculate for the unknown. First, calculating for the mole fraction of benzene, we need to find the product first of the mole fraction from the gas stream, which is 0.08, the gas feed rate, which is 100, the desired recovery, which is 0.99 all over 0.08 times 100 times 0.99, adding the oil fed to the column top. Calculating all of this, we get 0.0901. Jumping to letter D first, or finding the number of transfer units as NOY, we can use the formula here, YB minus YA all over Y log mean. For Y log mean, we can use this formula and get 0.01, where YA is equal to 0.01, which is 100, minus the desired recovery of benzene, which is 99%, times 0.08, which is the mole fraction from the gas stream, times 100, which is the gas feed rate, all over 0.01 times 0.08 times 100 plus 92. This will all be equal to 0.0008688. Now, we have the values for NOY. Substituting all of this, we get NOY as 7.8241. Next, for finding the KYA if the packed column height is given 3.35 meters. We will use this equation, the packed column height is equal to HOY NOY, to find the unknown. First, we need to find HOY. So we just find the ratio of the given packed column height over the NOY, which is 7.82 that we calculated here. Solving this, we can get 0.4282. We need to equate the HOY value to another formula, which is GM, which is the molar flow rate of gas, over KYA, which is our primary unknown. First, in calculating the mass flow rate of gas, we use the formula 1/2 times the quantity VA, which is the product gas, plus VB, or the gas feed rate, where VA here is equal to V prime times 1/1 minus YA, or the mole fraction at the product gas. Finding for VA, we get 92.08 kilogram mole per r square meters. Now, we can get the molar flow rate of gas. Substituting the available values, we get 96.04 kilogram mole per r square meters. We can now get for the unknown, which is KYA, substituting all the available values, we can get KYA is equal to 62.30 mole per cubic meter second. Next, the graph, our operating line somewhere here, which is y is equal to 0.879214x plus 0.0008688. For our equilibrium line, we are given y is equal to 0.45x. As we can see, we formed 5 triangles and a little triangle here. Using this graph to find the number of stages, we get 5.5 from the figure. And we tried it using analytical method, and we get n is equal to 5.74 stages, with a little discrepancy from the figure, which is 5.5. Calculating now for the minimum oil flow rate, we can get the product of 0.45 V. 0.45 is from our equilibrium line, and V is equal to the molar flow rate of gas. Calculating this, we get 43.214 kilogram mole R per square meter. In problem of group 3, we have water at 293 Kelvin and 1 atmosphere pressure enters a tower packed with 1-inch ceramic brill saddles. A gas flow consisting of an air per SO2 mixture enters with 10% by volume SO2. The design specifies that 95% SO2 is to be absorbed. The gas flow is equal to G 0.0007 kilogram mole per second, and the liquid, which is water flow, is equal to 0.055 kilogram mole per second. Letter A, estimate the tower diameter in feet and the pressure drop based on 70% flooding velocity. We are given tower here with oil or the liquid fed to the tower as 0.05 kilogram mole per second, and temperature and pressure, which is 293 and 1 atmosphere respectively. We also have the liquid feed rate as 0.05 kilogram mole per second. We don't have mole fraction, we are going to calculate it later. We also have the gas feed rate as 0.0007 kilogram mole per second, and a mole fraction of 10% by volume air per SO2. We don't have also product gas, which we will be calculating. Other specifications include 95% SO2 is to be absorbed, 1-inch ceramic burl saddles, and calculating first for the packing factor from table 14-13 using our handbook, we get 109.7561 per foot. The flooding velocity is given by 0.7, and calculating for the pressure drop at flooding, 0.12 times the quantity 109.7561 per foot raised to 0.7, we get 3.2172 in water per foot packing. Now, if there is not a specific flood curve, a pressure of 1.50 in water per foot is considered to represent an incipient flooding condition. We will use this 1.5 in H2O feet later on. We are required to find the tower diameter in feet and the pressure drop based on 70% flooding velocity. In finding the tower diameter first, we should calculate for the gas feed rate. We would base 100 liters of mass velocity with 10 liters of SO2 and 90 liters of air. Calculating for the mole fraction for SO2, we should get first the density using this formula and get 2.66 grams per liter. Calculating now for moles of SO2, we get 4.16 times 10 to the negative 4. For air, calculating for its density, we get 1.20 grams per liter. And for the mole of air, we get 3.74 times 10 to the negative 3. Now, calculating for the mole fraction at the feed, we use moles of SO2 over moles of SO2 plus mole of air. Substituting the available values we calculated, we have YB is equal to 0.1. For inert flow rates, we have V prime is equal to VB times 1 minus YB. Calculating for V prime, we get 6.3 times 10 to the negative 4 k-mole per second. We will later use these values. L prime is equal to LA, quantity 1 minus XA, which is 0.5 times 1 minus 0 equals 0.5 kilomole per second. For mass fraction for XB, we get 0.95 times 0.10 times VB here, all over 0.95 times 0.10 from here, times 0.0007 from here, plus 0.05, it's here. We can now get XB as 1.328 times 10 to the negative 3. Now, proceeding to SO2 balance, using this formula and this formula, substituting all the values we have to these formulas here, we get YA is equal to 5.52486 times 10 to the negative 3. Okay, for flow rates, for LA, we are given 0.05 kilogram mole per second. For LB, we will calculate using L prime, 1 minus XB. L prime, we calculated earlier, which is 0.05, times the quantity 1 over 1 minus 1.328 times 10 to the negative 3, we get 0.050066 kilomole per second. For gas feed rate, we have 0.0007 kmol per second. Calculating for the product gas here, we use VA equals V prime, which calculated earlier over 1 minus YA. So, substituting the values, we get 0.000633 kilomole per second. Okay, at the gas stream now, we will calculate for the molar weight of the product gas, which is 1 minus YA quantity times the quantity molar weight of air plus YA times the quantity molar weight of SO2. Substituting the values, we get the molar weight of product gas as 29.1364 kg per kilomole. For the molar flow rate of the feed gas, we get 32.4704 kg per kilomole. And finding now the density at the product gas and the density at the feed gas, we get, using the formula PM over RT, we get, substituting their respective values, we get 0.075598 pounds per cubic feet and 0.084207 pound per cubic feet. Getting its average density, we get 1.28131 kilogram per cubic meter. Getting the mass velocity at the feed and at the product by getting the product of VA and the molar flow rate. Substituting the values, we get 0.01844 kilogram per second and 0.02273 kilogram per second. At the liquid stream, we will use the same procedures to get the molar flow rate, the molar weight, at the product gas and at molar flow rate at the product liquid and molar flow rate at the feed liquid. We get 18.02 kg per kilomole and 18.0811 kg per kilomole. Finding the mass velocity, we get 0.901 kg per second and 0.904055 kg per second for the liquid fed and liquid product respectively. Getting its average, we get 0.9025 kg per second. At temperature, which is 293 here, we can calculate for the density of liquid as 998.1875 gram per liter using table 2-30 of our handbook. the velocity as 1.025 times 10 to the negative 3 Pascal second from the same handbook at table 2-313. And getting its ratio, we can calculate for the kinematic viscosity as 1.0268 centistokes. For the abscissa scale term, or the FLG, we use the formula, which is L over G, quantity the density of G over the density of L raised to 0.5. Substituting all the available values, we get the abscissa scale term as 1.57078. From the figure 14-48, we calculated the abscissa scale term as 1.57078. It is somewhere here. There. And then, like what I said earlier, we will use the pressure drop as 1.5. Here and then here, we can now see that our capacity parameter is equal to 0.6. Using the values we get from the graph, we can calculate for the capacity parameter. We can calculate for the U, or the superficial gas velocity, using the formula here, which is the capacity parameter is equal to the superficial gas velocity times the quantity density of the gas over the density of the liquid minus the density of the gas raised to 0.5 times the kinematic viscosity of liquid raised to 0.5. Substituting all the values we can calculate for the superficial gas velocity as 1.59537 feet per second. Finally, using the formula here for diameter, we use 4 times gm times mg over f superficial gas velocity pi rho g raised to quantity raised to 0.5. Substituting the values, 4 times 0.020585 all over 0.7 times 1.59537 pi times 0.3048 meter per foot times the rho, or the density of gas, 1.28131 kilogram per cubic meter, quantity raised to 0.5, we estimated the diameter as 0.2451 meter, or equal to 0.8041 feet. Using also the figure for 14.35 that we used earlier, we can calculate for the U flooding as 0.7 times 1.59537 is equal to 1.116759. Using this formula again that we used earlier, we can get the capacity parameter as 0.4199. And for the abscissa scale term, using the formula here, we can get 1.570787. From the figure here, we have abscissa scale term of 1.57078 somewhere here, and we calculated the capacity parameter as 0.4199. Finding the pressure drop from this graph, we have the abscissa scale term and the